Hi everyone, welcome to the first lecture on process design of production of biomethanol from biomass. In this lecture, we introduce the problem statement and we look at the interpretation thereof and then do the simulation of the first unit in the process, which is gasification of biomass. As a quick layout of the lesson, we will first look at the problem statement, requirements, given information such as design data and specification. Then we will start with a sequential process synthesis approach where we look at the first unit in the flow sheet or block flow diagram, which is the gasification unit. We will further perform Chemcad simulation of the gasification unit. Then lastly, we will look at cloning of components that are not available in Chemcad component database. The problem presented requires you to design a process to produce biomethanol from biomass through gasification of biomass to produce synthesis gas, which is a mixture of hydrogen and carbon monoxide, and further using the synthesis gas to produce methanol of specified purity. An initial block flow diagram is presented here. This is not a flow diagram. The process flow diagram will emerge from your design, but this is a simple concept to indicate to you of the possible process units. This block flow diagram will give us a starting point. Please note that as details emerge, the flow sheet will have pumps, compressors, heat exchangers, separators, recycles, and other units, as well as process layout schemes that will be dictated by the process synthesis procedure. The following design data and specifications are provided. The plant capacity is stated to be 500 kilotons per annum, that is of methanol, with an on-stream factor of 0.8, which simply means that our plant will be producing 80% of the year. This will help us calculate a number of operating days in a year, and we will use this information to calculate flow rates. The molecular structure of biomass in this scenario is to be taken to be that of sucrose, with all its physical and thermophysical properties. Gasification temperature is also given. The syngas coming from the gasifier is specified to have mole ratio of CO2 to CO of 1.1. We are also given the methanol synthesis reaction conditions, that is temperature and pressure. Furthermore, the following are specified for reactors. We are told to assume that the gasifier is a stoichiometric reactor with 100% biomass conversion. We are also required to find the amount of water required for the reaction and also to provide the full stoichiometry of the reaction in Chemcad. The gasifier will need to produce the gas with the given CO2 to CO ratio as specified. We are also told to assume that the water gas shift reactor will be an equilibrium reactor at a temperature and pressure that will improve the H2 to CO ratio to be 2 as required by the methanol synthesis reaction. For the methanol synthesis reactor, we are told to use the kinetic reactor with the kinetics provided. The real expression given is from Kuczynski et al. In their 1986 publication. In this design, we are not going to use our preferred methodology of overall mass balance process synthesis approach as we did in other designs such as dimethyl ether synthesis design. Although we know that the overall mass balance approach is the best process synthesis method to optimize reactants use and reduce waste, due to time limitations we will use a sequential process synthesis approach. In the sequential approach, we do not look at the overall process first. Instead, we start from the feed and look at each unit sequentially towards the product, and only then we look at recycling of any unreacted reactants. To start off with the sequential approach, let us look at the gasifier reaction. The gasifier reacts biomass with steam at elevated temperatures to produce a mixture of carbon monoxide, carbon dioxide, and hydrogen, which is the raw syngas. The reaction given below here occurs, where biomass reacts with steam to form CO, CO2, and H2. To use this reaction in Chemcad simulation, we need to have the stoichiometry fully specified, That is, we need to find coefficients A, B, C, and D. At the same time, we need to make sure that the ratio of CO2 to CO is 1.1 as specified. This means that the ratio of C to B has to be 1.1. This is a molar ratio, not the mass ratio. This ratio means that for every 1 mole or atom of carbon that goes into making CO, 1.1 moles or atoms will go into making CO2. The other way of looking at this is that for every 2.1 carbons that react, 1 will go to form CO and 1.1 will go to form CO2. Noting that carbon in reactants is 2.1 to form 1.1 carbon in CO2 and 1 carbon in CO. But in our case, where we have 12 carbons in reactants, like we have in our biomass, what would be the ratios A, B, C, and D? I will take you through the calculation to determine A, B, C, and D coefficients so that we have the stoichiometry fully specified. Then we can use the stoichiometry to simulate our stoichiometric reactor in Chemcad. Okay, let's move on. If we have 2.1 carbons forming 1 CO and also forming 1.1 CO2, what will 12 carbons form in terms of CO and CO2? We can use these ratios to solve for B and also C. What we can do is, if we do a ratio and say 2.1 over 12 gives 1 over B, then we can cross multiply to get this equation here and then solve for B. Similarly, we can do the ratios and then cross multiply to solve for C. We end up getting our B to be 5.71 and our C to be 6.23. The most important to do is, let's check if C over B is equals to 1.1, and calculating that, we find that C over B is equals to 1.09, which is approximately equals to 1.1. Please take very special note that we have to be very careful with the use of significant figures, as this will otherwise cause problems in Chemcad. The atoms may not balance depending on the significant figures you used in Chemcad. For example, if the acceptable error in Chemcad is of the order 10 to the minus 6, you may need to make sure that you provide your numbers to that accuracy or better. Here we have rounded off B and C to 2 decimal places. This already is likely to cause problems, but let's wait and see as we start to use these numbers in Chemcad. I'm hoping that I am wrong so that we do not have to handle long decimals in order to make Chemcad converge. The next step we need to do is oxygen atom balance to find out how much water will be needed. That is, we will have to calculate A. The reaction now looks like this, with A and D being the only unknown. Let us balance oxygen in reactants and products. We know oxygen in biomass is equals to 11 oxygen atoms. Oxygen in water is A, as there's 1 oxygen for water. And then oxygen in CO is 5.71, as there's 1 oxygen per CO molecule. And then oxygen in CO2 is 2 times 6.23, as there's 2 oxygen for every molecule of CO2. Therefore, then we can rearrange this balance and solve for A, which we end up getting to be 7.17. Then we end up with a reaction given below here, which the only unknown is D, which gives us how much hydrogen is produced in our reaction. The next and final step is to do the hydrogen atom balance to find how much hydrogen will be produced. That is, we will calculate D. The reaction now looks like this, with the only unknown being D, which gives us how much hydrogen is produced in the reaction. If we look at the hydrogen balance in reactants and products, we know that hydrogen in biomass, which is 22 atoms of hydrogen, and then hydrogen in water, which is 2 times 7.17, as there's 2 hydrogen for 1 molecule of water, and then hydrogen in the hydrogen gas that is produced, it will be 2 times D, because there's 2 atoms of hydrogen for every hydrogen molecule. We can then rearrange this balance to solve for D, which we end up getting to be 18.17. Then our equation and stoichiometry is fully defined as given below here. The most important thing is to check and recheck. With this equation as given, please check if the C, O, and H balance as it is. You may think that I'm just saying this. If you take this to Chemcad, you will have problems with Chemcad and with the mass not balancing, and you will spend maybe a couple of hours trying to sort out Chemcad, only to find out that the problem is in the stoichiometry that you are providing. And had you solved this, you would have saved yourself quite a bit of time. Now that we have a balanced chemical reaction, we can proceed to simulate the gasifier in Chemcad as specified in the problem statement. We will use a stoichiometric reactor with the reaction as given here, and also use the specified reaction temperature. It is important to note here that we can see from the stoichiometry that the ratio of H2 to CO is 3.8, which is much higher than the required ratio of 2. What does this mean? Does it mean that we do not require the water gas shift since we are already above the required stoichiometry of 2? I don't think so. I think that we can still use the water gas shift to now shift the H2 and CO towards making more CO, so that you now shift the ratio back to 2 by using CO2 and H2 to produce CO and water. This is your design. You can think what needs to be done. Is it worth getting an extra reactor, which is the water gas shift reactor, with all its accessories, such as addition of water, maybe temperature increase, maybe pressure increase, and then the separator downstream to shift the excess amount of H2 towards making CO, so that you produce more methanol in the end? Or you will use H2 as it is. It is a valuable product. You can use it either as a fuel source within the process, or you can sell it as it is to balance your economics. In this design, we will proceed with the water gas shift to shift the excess amount of hydrogen towards making more CO. To start off, let us use the feed of 1 kilomole per hour of biomass. We will come back to adjust this value to produce the required capacity once the entire flow sheet is complete. Let us use the gasifier pressure of 20 bar. We have not specified the gasifier pressure in the problem statement, but we know that gasifiers operate at elevated pressure. This will be a moderate pressure gasifier at 20 bar. Just to note that if we were using overall mass balance process synthesis approach, as I prefer in most cases, the throughput will be calculated from the beginning, as we will start by looking at the holistic picture of the process. Basically, what happens is you look at the overall outlook, the inputs and the outputs. That way, then you will be able to solve the overall mass balance. For this approach, we'll use mass ratios after we have completed the simulation to scale our processes to the required capacities. We'll come back to this later in coming lectures. For 1 kilomole of biomass, you know from the stoichiometry that we will need 7.17 kilomole per hour of steam. Let us supply the saturated steam at the gasifier pressure of 20 bar. So we are supplying saturated steam, which we can calculate the temperature of from Chemcad, or we can read it off from the steam tables. Okay, let us start with the simulation of the gasifier. You would remember from the Chemcad training videos that the approach is to start from left to right as you build your simulation. The first thing that we will do is we will start with the engineering units. The engineering units that we will use here, as you can see here, the default is English units. We will use common SI, and then let's check. We want our time in hour, mass in kilograms, temperature in degrees Celsius, pressure in bar, energy is fine. Everything here I am happy with. We will not change anything because the common SI units are sufficient for our simulation. However, if you have any problem with the units, you can always come back here and change the units. For instance, if you prefer the thickness, if you're dealing with pipes, you prefer the thickness of the pipes to be in millimeters, you can come and change that. Or otherwise, you can use the conversion of units within Chemcad. I trust that by now you have gone through the training videos for Chemcad and you are aware of all the tricks that I'll be mentioning within this lesson. Okay, the next step, we will go into selecting the components. We know that the first component is hydrogen, which we have here, and then we also have water. The next is carbon monoxide. Here we have. Then we have carbon dioxide. As you will notice that I am using different search keywords here. For carbon dioxide, I've used CO2 instead of like for water I typed WATER. Okay, then we'll add carbon dioxide. The next we need to add is sucrose, which is our biomass, and that, for as far as I'm concerned with the process components, this I think covers everything. No, we have forgotten our product, which is methanol. At this point we would not have methanol, so I'd rather leave it out for now. Okay, the thermodynamics wizard. Our temperature, we know the gasifier operates at a very high temperature. I think the temperature specified is 1150 degrees Celsius, so I will put 1500 as the high temperature. And then the pressure, I will just put 80 bar because our methanol synthesis operates at 80 bar. We would not be going that high here, but because our gasifier pressure is 20 bar, but I would rather choose to be 80 bar. The recommended thermodynamic methods are given as SRK, and the enthalpy also is calculated using SRK. We will agree with all the defaults for now. Then once the units are specified and the components are selected and the thermodynamics are specified, what we need to do now is to start building the flow sheet. You can take your time to build the flow sheet. What we know is that for the gasifier, you will be using a stoichiometric reactor here as given, and then you will feed in steam, and then you'll feed in biomass, and then you'll produce synthesis gas. I am not going to take you through building the flow sheet. I'm sure with the training videos you are fully equipped and skilled into doing that. I have already built the flow sheet, and then I will just move towards that. Okay, here is our flow sheet that we have built. Our stream 1 will be the biomass feed, and then stream 2 will be the steam feed, and then stream 3 will be the synthesis gas produced from the gasifier. Okay, we can start with biomass. I'm not going to name the stream, I'm going to leave it as it is. I will say we provide our biomass at 25 degrees, and then we'll provide it at the reactor pressure. The units that are given are kilomole per hour, and we know that we will be supplying 1 kilomole per hour of sucrose for our system. We can flash that to see if the stream is fully specified, and it is fully specified. Now looking at the stream, which is stream 2, we know that our pressure is 20 bar, and we are supplying saturated steam, which means that the vapor fraction of the steam will be just at 1, and the flow rate of steam also is given in kilomole per hour, which is 7.17, as we have seen from the stoichiometry. Then we can flash this to see if it's complete, and then we get the temperature, the saturation temperature of steam at 20 bar. You can confirm with your steam tables to see if this is correct. That concludes the specification of the feed. The next step, now let's specify the reactor. Let's go with an isothermal reactor operating at the given temperature of 1150. I will just have to quickly go back and look at the specification before we proceed, to just make sure that the specifications that we are stating, that yes, we have 1150, and then going back to Chemcad. The key component that we are going to be using is sucrose, and the fractional conversion is 100%, which is 1. And then the next thing that we need to do is to specify the reaction. The important thing to note in Chemcad stoichiometric reactor is the reactants are specified as, the coefficients of the reactants are specified as negative numbers, and the products are specified as positive numbers. As you can see from here, we already have a problem because we don't have carbon monoxide. We will have to come back and change that. Let us just cancel and go to look at our components. How did we miss carbon monoxide? Yes, we don't have carbon monoxide. Let's just go CO. There it is. Then we can add it. That's okay. We go back to our reactor. It's 1150, and then key component is still sucrose. Fractional conversion is 1, and then we have to bring our stoichiometry here so that we can see it, so that we can enter it correctly. The stoichiometric coefficients are in mole base, which is okay. Let us bring the stoichiometry, the last slide we worked on. It is this one, and then let us bring there. Okay, you can just move it aside. For water, we know that it is sucrose is -1, as it is a reactant, it gets consumed. Water is -7.17. It's a reactant, it gets consumed. Hydrogen is 18.17. Carbon dioxide is 6.23, and carbon monoxide is 5.71. Remember, I made a big deal about this being rounded off to 2 decimal places, and Chemcad may give us problems when we need to solve this, depending on the accuracy and if these numbers balance according to the mole balance. We will see that if that holds, but at this point we can proceed. Okay, that's our reactor fully specified. The next thing that we can do is try and run it and see if it will give us the product that we require. Let's do run all. Run has finished. You can hover over the stream and see if everything has been calculated. As you can see, the hydrogen produced, all the water has been used, all the sucrose has been used, all the carbon dioxide produced, and the carbon monoxide produced. So The stoichiometric coefficients we have do not have to be changed because they balance perfectly in the significant figures that we have produced, we have supplied, and Chemcad does not seem to have a problem with that, and we have to be happy with that because now we don't have to enter numbers with long decimal places. So at this point, our gasifier works well and the simulation is complete. We can proceed to the next phase of the lecture. In this section of the lecture, we are going to look at if the compound that you are given, the biomass compound that you are given, is not available in Chemcad component database. For example, if you are given cellulose, hemicellulose, lignin C, lignin H, and lignin O, which I know for sure that they are not available in Chemcad component database. For any biomass represented as component that is not available in Chemcad, we can clone the new component using a known component. For the purposes of the study, we will use sucrose as our original component that we would use for cloning, which means that all the components that will be cloning, cellulose, hemicellulose, lignin C, H, O, will have properties, both thermodynamic and physical, that of sucrose. We can adjust them and change them if we want to, but for the purposes of this design, we are going to leave them all the same, which are going to be that of sucrose. The only thing that is going to change is the molecular formula and the molecular weight. In Chemcad, where you would do this, you would go into the thermophysical menu and then you click component database. On the expanded menu, you click clone component. In the available components tab, you can search for sucrose or any other component that you want to clone. For us here, we'll be cloning sucrose. You can then select sucrose and click OK to continue. In the destination database tab, click OK to continue, which basically tells you where the database, the component that you are writing would be written into or would be stored in. In the View or Edit Component tab, click on the Synonyms tab to continue and edit the synonyms or the names of the component that you are cloning from sucrose. In the View or Edit Component Synonyms, type the standard name of your new component, in this case lignin H. Clear all the other synonyms 1 to 8 and leave them empty. You do not need them now. You will notice that sucrose had all the synonyms, but you don't want to have a lot of synonyms for your lignin H. As you can see here, I had made synonym 1 to be sucrose clone. Do not do that, just leave the standard name. The most important thing is do not change the case number, because you may end up interfering with other components which may have the same case number as you are changing towards. So leave the case number to be that one of sucrose, is fine. Click OK to continue. This will take you back to the View or Edit Component tab. Then you can click on Formulas. In the View or Edit Component Formulas, change the formula which would originally be that of sucrose to be that of lignin H, which is C22H2809. Click OK to continue. You may think this sounds very silly, but make sure that the oxygen is O, not 0. I had made that mistake before, and Chemcad continued with H being the molecular formula being C22H2809 hydrogens. Please make sure that you are not making the same mistake. A notification tab will pop up as you click OK to inform you that the molecular weight does not match that of sucrose. Remember, we have changed the molecular formula, so therefore the molecular weight will change. That's alright. Remember, that's what we specifically wanted to change. Click Update to continue. In the View or Edit Component tab, click Exit, because we are now finished with all the editing that we needed to do. As you can see here, you have a number of properties that you can change the basic data, the density data, the vapor pressure data, the heat capacity data, viscosity data. We are not going to touch any of those because we are going to leave them to be that of sucrose. The only thing that we wanted to change was the molecular formula and of course the main. A notification tab will pop up when you click exit to inform you about the changes you're about to make. Ensure that the radio button is on the first option as indicated here by this arrow. Click OK to continue. A notification tab will pop up to inform you about reinitialization of streams. Click yes to reinitialize and to continue. Your new component has now been added and you can access it just like any other of the built-in components in the Chemcad components database. Go to the thermophysical menu and click select components. In the select components tab, search for your new component using the keyword. In this case, the keyword you can use is lignin, and your component will come up. As you can see, I had added the synonym that I've added basically came in as well. And then earlier on I had added lignin C, it will also show up here. You can select the components that you have added, which is lignin H, and then add it to your list of components, and then voila, you are done.
Thank you very much for studying with Tutor.me Open College. Please click subscribe so that you are kept updated with new learning material as it is being updated. If you like this video, also, please click like so that the video is recommended to other learners such as yourself.